Hello, my name is Darren Thomas and I am the Director of Educational Research Techniques. In this video, we're going to be taking a look at implicit differentiation. So let's go ahead and get started. So this is a little bit trickier to try to explain, but we're going to do the best that we can to try to help you to understand implicit differentiation. So a little bit of background. So we're all familiar with such an example as y equals x squared plus 1. In this particular situation, the y variable here is a function of the independent variable x. And so another way to say this is that y is an explicit function of x. That is what's happening here. So in other words, it's clear what the relationship is between these variables here. However, in a different example, if you look at this one right here, we have y minus x squared equals 1. This is a slightly different situation in that y is not expressed in terms of x. So that's what's happening here. Y is the equation, so in terms of x. So because what's happening is that y is being defined in terms of x implicitly. In other words, it's implying that there's a relationship here, but it's not stated in a way where it is clear. It's implied, it's not explicit. So when we're talking about explicit, it's clear of the relationship between the variables. So y equals x squared plus 1 in the first example. In the second one, it is not so much as clear what the relationship is. You would have to do a little bit of algebra to rearrange the variables to make it an explicit situation. So the purpose of doing this, and so the purpose of doing this implied thing is that when you're in a situation like this, there are tools you can use where you can still find the derivative, and that is implicit differentiation. And so if we do this when we want to try to find a slope to a curve, or or functions that fail what they call the vertical line test, something we've talked about in the past. All right, and so this is kind of what's happening. Let's go ahead and move on here. Now, here's our example that we're going to go through here. We're going to go through the following guy right here. X squared plus y squared equals 16. Now, we're going to be using some slightly different notation to do this. In the past, we've always used this notation right here, y prime. And this is known as, let's see here, Lagrange notation. So this is great, Lagrange. The spelling is not as important here. Now, what we're going to be using now going forward, at least in this particular situation, is something called Leibniz notation. So that's going to be known as dy over dx. That's what's happening here. And so this is another famous mathematician, obviously, Leibniz, who helped to develop calculus. So this is talking about the derivative of y in respect to x. I guess I should make this an x down here. And sometimes we'll say the derivative in respect to x, derivative of d over dx. All right, that's what we're going to be using going forward. So getting back to our point here, this is what we're going to be doing. So what we're going to do is as follows. We're going to take the following example here. So derivative of respect to x here, and it's going to be x squared plus y squared. Put that all in parentheses, equals derivative in respect to x. Oh, not an equal sign, whoops, of 16. So we just do some basic ideas here. We do the sum rule here, and over here we have the constant rule, so this is going to become 0 over here. And we're going to split apart this x squared plus y squared because the sum of the derivative is a derivative, something we like to do all the time here. So derivative respect to d of x, x squared plus the derivative respect to x of y squared, there we go, equals 0. Now, we're just going to go through the process of actually finding the derivative here. So the derivative in respect to x of x squared, well, that's going to be 2x. Now, the derivative of y squared, this is where it gets a little bit complicated, is going to be 2y, and then we're going to have the derivative of y in respect to x. And so you're probably wondering what is going on here, and it's a little bit of the chain rule that is happening. And so what is happening is that essentially what we're doing is something along the lines of this. So let me see if I can make this as clear as possible because it's really kind of weird and hard to understand. We're using the chain rule. So we're kind of going something like this. We got mx raised to the nth power, and then we want to find the derivative of this. Now, inside this particular example, we have two things going on here. We have x squared, and then we have mx. That's kind of what's happening here. And so in this kind of a situation, what happens is that you find the derivative of y squared, and then what happens is that you have this leftover guy here, the derivative of y in respect to the of x. That's what's happening. And so you end up with something along these lines. So if I were to put in some actual numbers here, it would be something like this. Again, this is really kind of abstract here, but let's just see if we can work through this together as best we can. So my original guy here was y squared. So it was y squared. So you could really say 1y squared. That's kind of what I was working with. And so you can see what's happening here. So oh, I forgot to back something up. So if I were to work this out first, let me show you what's going to happen here. So again, using the chain rule, I'm going to have n, because I bring that down, times mu, that's what we're just using here as an example, x to the n minus 1, and then we're going to multiply that by, I'm going to write it down here below, the derivative of mu, that's supposed to be a mu here, x. All right, that's what's going on. So now to work this out, I essentially have, to make this as simple as possible, I have 1y squared. That's what I kind of have here as my derivative. And I'm looking for the derivative of this guy right here. So I'm going to put d dx. So that's going to equal as follows. So if you look closely here, I have a 1 here in the front. Excuse me. I have let's see here. So I'm going to bring the n down. So that's going to be a 2, like so. And then my mu is just going to be, y squared 2 times 1. Oh, 2 times, we're going to put a times 1 here. Okay. Then we're going to have our y like so. And it's going to be 2 minus 1. So this is what's going on. My mu here is 1. That's that first guy right here. And then I bring the 2 down. And so then I multiply this by mu, whatever that is. That's going to be just y here. But I don't really have the derivative yet. So I'm going to put d of dx, kind of like dy of dx, like so. And that's kind of what we end up having here. And so when you work all this out, you end up with essentially, you have the 2y here, like this is where this comes from, 2y. And then over here you have basically y dy of dx. That's what we call it. This is what's happening. Again, this is really, really tricky, but we're using the chain rule here because we have these two functions inside here, a nested function. So the mx, which when you do the derivative of that, it just becomes the x by itself, and then, the x by itself, and then you have the exponent at the top. So again, we're trying to do the best that we can to make this as clear as possible. But let's see if we can start to wrap this up. So when we continue our experience here, we end up with the following. And again, we use the chain rule. But in general, let me go back here. What we normally do is we don't work this out by hand unless there's a really specific reason. Generally, what we do is we just kind of plug in the d dx here, and we end up with this 2y dy dx like this. This is just kind of like the shortcut. So normally you don't have to calculate it by hand. Now, moving on, you're going to have 2x plus 2y, and then you're going to have the derivative of y in respect to x, like so. And then this is, of course, going to equal 0. So we're getting really, really close here. So now we want to isolate. We want to isolate this, the derivative of y in respect to x here. We want to isolate this guy right here. This is our goal right now. And so the first thing we're going to do is we're going to move the 2x to the other side. So 2y, 2y dy in respect to dx is going to equal negative 2x, like so. And then, of course, now I think we know we divide both sides by 2y, and And so you end up with the derivative of y with respect to x equals negative x over y. And this is our answer. So you can see how this gets really, really complicated. But what we need to remember is that when you are finding the derivative of the y term, you always end up with the actual derivative plus the derivative of the second term in respect to x. That's what's happening here. And so again, because I know that this was a little bit unclear right here, when you're working with this, it always kind of converts to this. And this is whenever you're dealing with the y term almost always. I haven't seen an exception of that yet. So when you get to this point, a lot of times they switch the notation, which makes it very, very confusing. And you know, with dy y prime, that's what you end up with. Because again, you're doing the chain rule over here to try to find out the derivative of y in respect to x. That's what we're trying to do. And so you kind of almost do it implicitly. You don't have to do it explicitly a lot of times. A lot of times if you look in books, they just skip this step and they just put y prime. And you're like, where did it come from? Well, it came from this process over here, this mu x to the n, where you're trying to find the derivative of this. And so, you know, you have two clear functions here. You got the mx, and then you got also the where it's raised to a certain exponent, an n exponent. And then when you work out that, you end up with this guy down here at the bottom, which is hard to understand, but it is a critical step in this process. And so when you finally do that, your next job is to want to isolate the derivative of y in respect to x, and then you're able to work things out. So that is a very, very simple way, a very, very simple example, of the process of implicit differentiation. A complex idea that is very useful when you start dealing with things with curves and things and circles and other things of that nature. So my name is Darren Thomas. I am the Director of Educational Research Techniques. Take care.